Good morning students. Today I am going to explain about optical fibers. In this video I will explain what are optical fibers, principle, propagation of light through optical fiber, acceptance angle and numerical aperture. Coming to introduction of optical fiber. The optical fiber is a waveguide or a medium which is used for transmission of light. In fiber optics communication, light is used as carrier wave because light is having more frequency, that is of the order of 10 to the power of 15 Hz, and hence possess more information carrying capacity than radio waves and microwaves. But these light waves cannot travel far in open atmosphere as the energy gets dissipated rapidly. Hence, some guiding medium is needed, which is called optical fiber. Because of high information carrying capacity and low attenuation, nowadays optical fibers are finding wide applications in telecommunications, local area networks, sensors, computer networks, etc. These optical fibers carry much more information than copper cables. The transmission of light waves through optical fibers was first demonstrated by John Tyndall in 1870. Now coming to the definition of optical fiber, it is a very thin cylindrical structure of glass, plastic or any dielectric medium which transmits the light beam from one place to another place with low losses of energy. Now coming to the structure of optical fiber, it mainly consists of three layers. First one core, second one cladding, third one buffer jacket. Now we will discuss one by one. First one core. The innermost cylinder is called the core and it has higher refractive index, say N1, and it carries the light and it acts as a denser medium. Next one cladding. The core is surrounded by another cylinder which is called cladding. It has lower refractive index when compared with core refractive index. Let it be N2. And it acts as rarer medium and it helps the light within the core because of N1 is greater than N2. Next, third one, buffer jacket. Cladding is surrounded by buffer jacket which will protect the optical fiber from moisture and it also provides strength to the optical fiber. Now coming to the principle of optical fiber. The main principle involved in the optical fiber is total internal reflection. We know that a light beam undergoes total internal reflection only when it satisfies two conditions. First one, when the light ray is traveling from denser to rarer medium only, it undergoes total internal reflection. Second one, angle of incidence must be greater than critical angle. Then only it undergoes total internal reflection. That I am showing in these diagrams. Look at these diagrams. Here I am showing two media, denser medium of refractive index N1, rarer medium of refractive index N2. And XY is the boundary between these two media. AO is giving us the incident light ray. When it strikes the boundary, a part of that one will undergo internal reflection and the remaining part undergoes refraction. Here OC is giving us a refracted ray. Let I be the angle of incidence and R be the angle of refraction. As the angle of incidence increases, the angle of refraction also increases. More and more it bends, means the refracted ray bends away from the normal line. When the angle of incidence is equal to a particular angle which is called critical angle, then the light ray refracts along the boundary between the two media. That is, it travels along XY. Now the critical angle is defined as the angle of incidence where the angle of refraction is 90 degrees. Suppose the angle of incidence is greater than critical angle, then the incident light ray undergoes total internal reflection. In this case, apply Snell's law at the boundary of two media, then we will get, I think we know what is Snell's law. Sin I by sin R is equal to N2 by N1. Then N1 sin I is equal to N2 sin R. Here I is angle of incidence, R is angle of diffraction. Then N1 sin theta C is equal to N2 sin 90 degrees. Here theta C is critical angle and angle of refraction is becoming 90 degrees. Then N1 sin theta C is equal to N2. Therefore sin theta C is equal to N2 by N1. Therefore critical angle theta C is equal to sin inverse N2 by N1. Now we will discuss about propagation of light through an optical fiber, acceptance angle and numerical aperture. So here we have to discuss how the light wave propagates through an optical fiber and what is this acceptance angle we have to define. So for that sake, let us consider an optical fiber which consists of core of refractive index N1 and cladding of refractive index N2. Let N0 be the refractive index of launching medium. Launching medium means the medium which is outside of the core, means the light ray enters into the core from this launching zone. Let I be the angle made by the incident ray with the axis of the optical fiber. Here this axis of the optical fiber is shown by dotted line, and let R be the angle made by the refracted ray with the axis of the optical fiber. Let theta be the angle made by the refracted ray at core cladding interface. Now, if theta is greater than critical angle theta C, then the ray undergoes total internal reflection at the core cladding interface. As long as theta is greater than theta C, the light remains within the fiber by means of total internal reflection. Now apply Snell's law at the launching phase of the fiber. Then we will get N0 sin I is equal to N1 sin R. Now from the right angle triangle ABC, we know that R plus theta is equal to 90. Therefore R is equal to 90 minus theta. Now substitute this R value in equation 1, we get N0 sin I is equal to N1 sin 90 minus theta. This is equal to N1 cos theta. Therefore sin I is equal to N1 by N0 into cos theta. Therefore this is equal to N1 by N0 under root 1 minus sin square theta. Now apply Snell's law at the core cladding interface. N1 sin theta C is equal to N2 sin 90. N1 sin theta C is equal to N2. Therefore sin theta C is equal to N2 by N1. Already we derived that one in the last sheet. If theta is equal to theta C, then I becomes maximum, which is called acceptance angle. Substituting this in equation 2, we will get sin I acceptance, means here that I maximum is also taken as I acceptance, means which is called acceptance angle. Sin I acceptance is equal to N1 by N0 under root 1 minus sin square theta C. Now substitute sin square theta C value, and after simplification we are getting sin I acceptance is equal to under root N1 square minus N2 square by N0. Here N0 is the refractive index of launching medium. Suppose the light ray is entering into the core through air medium, then N0 becomes 1. Therefore, sin I acceptance is equal to under root N1 square minus N2 square. This is also known as numerical aperture. Therefore, acceptance angle is equal to sin inverse under root N1 square minus N2 square, where N1 and N2 are refractive indices of core and cladding. Now, giving to the definition of acceptance angle, it is defined as the maximum angle made by the incident ray with the axis of the optical fiber so that it undergoes total internal reflection after entering into the core. Suppose if the light ray makes an angle greater than acceptance angle, then the light ray will escape from the side walls of the optical fiber without undergoing total internal reflection. So, always the angle of incidence must be less than or equal to acceptance angle. Then only the light propagates through the optical fiber from one end to another end. Now coming to the numerical aperture, it is defined as sine of the acceptance angle and it represents the light gathering power of the optical fiber, and this numerical aperture is equal to sine I acceptance is equal to under root n1 square minus n2 square, where n1 n2 are refractive indices of core and cladding. Okay, thank you.